Lecture problem 3. A car traveling at a constant speed of 30 meters per second passes a highway patrol police car which is at rest. The police officer accelerates at constant rate of 3.0 meters per second squared and maintains this rate of acceleration until he pulls next to the speeding car. Assume that the police car starts moving at the moment the speeder passes his car. Determine the time required for the police officer to catch the speeder and the distance traveled during the chase. First, let's sketch this chase by means of a very simple diagram. The speeding car is moving at constant speed of 30 meters per second all the time, but at the moment when the speeder passes by the police car, starting from rest, start accelerating and chase the speeder. At some point in time where the red line is located, the police car is going to catch the speeder. Clearly this question is a kinematics one-dimensional question, and it does require a system coordinate. The x-axis is going to be set up along the direction of motion, where the origin of that system coordinate is going to be where the police car started chasing the speeder. Since the speeder is moving at constant velocity all the time, his motion is going to be controlled by the constant velocity equation, where x equals x naught plus vt, where the v is the 30 meters per second. Substituting the x0 and the v by their respective values, we obtain x to equal 0 plus 30 times the time t. In other words, x equals 30 times t. Notice that there are two unknowns, the position x and the time t it takes the police car to catch the speeder. As far as the police car is concerned, the motion is an accelerated motion, and the best kinematics equation that could be used to match the motion of the speeder is that one that relates the displacement versus time, and that equation is the one that says x equals x naught plus v0 t plus 1/2 a t squared. Notice that the common quantities between the speeder and the police car are the displacement x minus x0 and the time t. The velocity of the police car at the moment when he catches the speeder is not the same as the speeder. The police car must be moving at a very high speed at that moment. Substituting the known quantities, we obtain x to equal 0 plus v0 is equal to 0 times the time t. That is going to lead to 0 plus 1/2 times the acceleration of the police car, which is 3.0 meters per second squared, times the unknown time t squared. Simplifying this equation further, we obtain x to equal 1/2 times 3, that's 1.5 times the time t squared. To be able to solve for the time, all we need to do is to equate the following two equations. 1.5 times t squared equals 30 times t. This equation can be mathematically solved by moving the 30t to the left-hand side of the equation. Therefore, 1.5 t squared minus 30t equals 0. Factorize the time t, you obtain t times 1.5 t minus 30 equals to 0. One of the solutions is the time t equals to 0 seconds, and this time represents the beginning of the chase where the police car and the speeder were side by side. We are not interested in this time. The other time is obtained by making the 1.5 t minus 30 equals to 0. Solving for this time, we obtain 20 seconds. And this is the time that represents the moment where the police car catches the speeder. Now that we have solved for the time t, we can solve for the position x where the police car catches the speeder by either using the equation of motion of the speeder or the police car. The equation of motion for the speeder is a much easier equation, x equals 30 times t. Substituting the time t by 20 seconds, we can solve for the position x to equal 600 meters. This position x represents also the magnitude of the displacement as well as the distance traveled by both speeder and the police car, because this motion is a one-dimensional motion where the two objects are moving in one direction all the time.